right, hey everybody. I know it's been a while since I made a video, but Spectronaut came out with a new version of Spectronaut 19, I think. They're on 19 point something, I don't know. 19.024, it just came out a couple weeks ago at ASMS, so I thought this would be a good opportunity to look at some of the new features. And they have some, I wanted to demonstrate the normalization that Spectronaut's doing, because I know some of you had questions about it. So I did a really kind of simple experiment, my poor pipetting skills notwithstanding. So anyway, what I did in this experiment, and we're going to do both at once. We're going to look at the normalization of how Spectronaut is working, and we're going to look at some of the new features. So what I did in this experiment, and all of this data is going to be available on our BioShare system. I will post a link to that in the video. And basically what I did was I took a simple 50 nanograms of HeLa, loaded it on an Evo tip, ran it 100 samples per day. We used our Opentrons 2 to load it. That may be the issue with some of the samples, or it could be my terrible pipetting. I don't know. We'll see. And so I did that 4 times, and I also loaded 200 nanograms 4 times, put that in Spectronaut, and we'll see how the normalization works. So just to give you a little update, a little background on what normalization is. The normalization here, you could see that under post-analysis normalization. And basically what it does is it tries to correct for differences in loading. So for example, usually this is, you try to load the same amount of material in a proteomics experiment, except if you're loading by volume, if you're doing like affinity purification, or there's some other experiments where you're not going to load equal amounts, but for the most part, you load equal amounts. And so what this does is it kind of corrects for pipetting errors or other errors in your protocol. Maybe your robot or something is pipetting things a little differently. And so what this does is normalize the signal across the experiments. And you can see right here, we have the 50 nanograms and the 200. And this is a log 10, so it's not going to look like it's 4x. But then it normalizes the response so they're all even. And you may ask, how is it doing this? Very good question. It has different ways of normalizing. So let's look at the settings and see what it's doing by default. Okay, so how we get to the settings is we do the gear here under analysis. You open your tab, and then you go settings, and we'll give it a second to pull up. And let's see here. The normalization will be under the quantification tab. And you can see right here, cross-run normalization is checked. We're going to uncheck this in a minute to see the difference. And we can look at the advanced options too. Let's see. Oh, and we're going to turn off deep quant for now, because we're going to turn that on later. But let's look at the normalization, cross-run normalization. It's currently turned on. You could turn that on and off by clicking this link, clicking this little checkbox. Normalization filter type. So let's say you have 2 FASTA libraries or 2 FASTA files, which is the database we use to keep our protein sequences in. Or library filter name. If you're doing 2 different libraries, you don't have to concern yourself about this. That's kind of a mass spec thing. But anyway, if you have 2 different FASTA files, which means let's say you have human, you have like a dual species thing where you have human and E. coli spiked into it, and you tell it just to normalize on the human because you don't want it to normalize on your other species too. Or another example would be if you have like an expression protein that you know is in every experiment at the same amount, or else it should be, you could tell it just to normalize on that protein or a series of proteins, and then not normalize based on all the signals. So that's kind of what that is. Row selection can be identified in 1 run, or identified in all runs, or identified in a percentage of the runs, and you can put in the percent here. You may want to experiment with that. Let's see what automatic is. Let's see. Selects the precursors. I don't really know what it's doing. It says automatic. What does it mean? I don't know what it does by default. Maybe that's in the manual somewhere. Anyway, we can look that up and see, or I can ask. Um, multi-channel Q-value filter. Gosh, I have no idea what that means. Multi-channel Q-value filter. I don't know. Maybe that's for like a SILAC experiment or something. The other normalization feature is by modification type, and usually that's used specifically for phosphorylation enrichment, and that's usually turned on by default if you do the PTM workflow for phosphorylation, and it assumes that it's enriched. So if you have enriched for phosphopeptides, people think it might make sense to use just to normalize on the phosphorylated signals instead of all the signals, because you assume if you're enriching, most of your signals are going to be phosphorylated anyway. Okay, so we're going to leave that on. Deep quant was turned on, but we're going to turn that off, and because we're going to play with that later. And that's only for timsTOF stuff anyway. So you can easily turn normalization on and off. In the settings tab, you can do this with the viewer. So it's really nice. And the only thing you're going to be out is time. Or your experiment's going to be screwed up if you normalize it incorrectly. So normalization is important. So give it some thought how you're going to do it. Okay, so let's see. See, it only takes a few seconds to do this. And then let's go look at the post analysis. And you could see here's the 50s and the 200. And it normalizes it together. And you could see these are my 50s. This is the tick. The total ion chromatogram, and you want these to be the same if you're loading the same material. Do you see there's something kind of wrong with this one? Could have been my poor pipetting skills, could be the Opentrons robot, which doesn't make the sandwiches all that consistently sometimes. And for those of you who don't have an Opentrons robot, you're probably like, what the hell is he talking about? But for those who do, you know what I'm talking about. And then these are the 200s. Okay, so let's look at some proteins, and these should be normalized. And so we can look at the volcano plot, and you can see here's the one that looks a little different. So that's my 50. That's probably not very good. And we could look at the principal component analysis to see how they're clustering, and you can see the 200 nanograms cluster a lot better than the 50s, and that's probably due to the Opentrons or pipetting. So if I had a better pipette, maybe the 50s would cluster better, or maybe not. We'll see. I'm going to repeat it and see what happens. But because this is normalized, you don't expect very much differential expression because it should normalize everything together. And we could see if it does that. And you can see it doesn't really. So even with normalizing, there's still a lot of differential expression here. Which shouldn't happen, but that's just proteomics, so it's good to test. So this is kind of what happens. And so what else can I show you? And then there's some candidates here. So even when it's normalized, even with a 4-fold change, you do see some differential expression. So you could turn off the log scale, which I like. And you could see you don't expect these to be more in the 50s than the 200s, but this is a contaminant, so who knows what it's doing. Why these are more in the 50s than the 200s is anybody's guess. I don't know. It's probably some weird normalization thing. I don't know. We could look at the volcano plant. You could see most 20/50 are going in this direction. I wish you could click on these, but you can't. So even normalization doesn't really solve anything. It doesn't solve everything. It can solve some things, but you do kind of want to put the same amount of material in there. So let's look at what I like to do is we can go into the analysis view, look at this, and we're just going to pick a good signal here. These are the proteins we identified with the precursors. So we're just going to do this one and try to find something with a good signal. That's okay, probably on the lower end of, let's just look. That looks like a nice one. They're all pretty nice, but the ones with the higher signals are going to be quantify a little bit better. That looks pretty good. Okay, so what we're going to do is remember these should be normalized. And the plot I like to look at is I like to open this display new plotting window. That will kind of open here. And what I like to do is go cross runs. So this will view the data across runs. And I like to look at precursor versus protein quantities. Oh, that's really weird. Why are these? I think the normalization, right? These should be. This is a little better. For whatever reason, it is normalizing these. Where did it go? It all kind of looks like there's more in the 50s and the 200s, right? It's probably a normalization artifact. Maybe we could see if we can fix that. But let's not try and fix it for now. Let's see. Okay, so you can see it kind of looks like it over normalized it, so it looks like there's more signal in the 50s than in the 200s. So that's not great. And another thing we want to look at is looking at the LFQ bench, which sometimes works. And you can see the average log2 ratio, which we expect 0, is close to 0, but not exactly on 0. So you can see there's kind of a skew this way. And this is just the bovine contaminant. So we're kind of just looking at the humans here. And you can see this is kind of an M over A plot, which is the log2 of the abundance. And the tighter this is around 0, the better. So if we normalize it, we expect everything to be around 0. And as we go in this direction, this is kind of the signal to noise of the signals we're measuring. And the lower the signal to noise, you can see the spread increases, as you can imagine. So the lower the signal to noise, the more error you're going to get in your quantitation. Okay, so I don't know, we could play around with this and see if we can do some things to the normalization to try and fix it. Cross run, that looks good. Precursors or protein. So if these were normalized correctly or pretty correctly, we would expect these to be more stable. Like we would expect all of these to be the same, which, you know, doing a 4x difference between, you know, the samples is probably a little too much for it to expect. But we can see if we can change it. And so we go back to this again, and we go to normalization filter type. You know, we can select FASTA name. We're gonna have to figure out the FASTA name, but there's not a lot of bovine sequences in here, so it doesn't really. I don't think that would really matter. Imputation, like normalization strategy. So I think the default is global, right? So it clicks global if there's less than 500 equals local. So it's doing local by default, and there's a paper in here you can read. Row selection, I don't know. We could say identify in all runs complete. I don't know what it does by default, right? And so we could see if that makes any difference. And the best plot to see if that made any difference is this one. Yeah, maybe. I don't know. It looks a little bit more towards 0 than the other one. I could have taken a screen capture to check, but it's closer to the 0 line. Maybe that helped. And we can go back here and say across runs. And I'm going fast as usual, but you can pause it and rewind. And we can look at, can you rewind a YouTube video or go backwards? Okay, so let's see. Why can that not be displayed? Okay, probably because we'll just pick something else here. Oh, there is a lot of bovine in there, huh? You can see if that makes a difference. Precursors, let's look at, that doesn't look too good. Let's pick something. This one again, and cross runs. It's already displayed. All right, so you can have multiple ones of these open. Okay, that looks better, right? So these should be 50, these should be 200. It looks like that improve things. Let's look. Let's see if, okay, that looks good. Let's see that. Okay, that doesn't, well, you're still a little bit higher in the 50s, so let's see. Okay, that looks okay. And what you do expect is, because when you have multiple precursors for protein, you expect your protein quantitation to be more stable than your precursors. That's what I would expect anyway, especially as the precursor signal gets more in the noise. This is actually a pretty good signal, but you could see the proteins are stable, and that's stable. Okay, that looks good. So anyway, it looks like changing the precursors to full looks like it made a good difference in this data set. Anyway, so you may want to play around with that. And let's turn on, there's this new feature in 19 called Deep Quant, and it's only available for timsTOF data. So if we acquire the data on your on the HT, that should be available to you, and you can hover your mouse over this. So Spectronaut has a lot of hovering. Applies interference corrections computed by our deep quant model, whatever that is. In limited testing, it improves candidate discovery on the timsTOF HT. And so before we do that, let's look at the volcano plots again. That looks a little better. Still a little bit skew this way. That's the same. And you could see the candidates. Let's see. Log scale. This should not be less in 200 than 50. So that's probably a normalization artifact. I don't know. Let's try it and see. So we're going to go back to the analysis tab, hit the gear. You may want to play around with this. I'm probably not going to turn it on by default, and I'll tell you why. So then we'll turn it on again. Okay. Let's give it a couple minutes. All right. Now let's see if that looks better. Okay. Let's look a little better. Still. You can see the candidates decreased. If you go back, it was like 500, and now there's 300. All right, so let's go look at the LFQ bench again. Okay, so maybe it's a little centered more on 0. That's what you would expect if the normalization's working the way it should. And again, 4x difference is probably a little too much for the normalization. Okay, then we'll go back and we'll just select some precursors again. Uh-oh. Third window, go back, cross runs. And by the way, this precursor versus protein quantity seems to be a new feature in 19, which I do really like. Ooh, that looks nice. Okay, kind of a janky signal, but we'll see. All right, that looks okay. Get a little up more in the 200. Okay, not bad. And you can see how the precursor is less stable than the protein, because we have 10 precursors for this protein. Let's look at that one. That doesn't look very good. Those signals don't look very good. That one looks okay. Let's see. You could see this is kind of going up in the 200. Protein is stable. All right, that looks good. Okay, we expect the proteins if the normalization's working. And that looks good, that looks good. So maybe deep quant has helped something here. Let's see. So anyway, you may want to turn it on by default. It seemed to help the normalization correctly. And as far as I know, what deep quant does is you can see how it uses the, so these elution groups here, these are the fragments or the product ions from the peptide. And again, these are the precursors. You could go back to my earlier videos to look at that. And I believe DeepQuant helps pick which one of these to use because there's a lot more B and Y ions than just these. And so it helps pick, especially after things are noisy. And you could see how um, these are kind of dashed, and that means it's not using them. So that's the interference. So it takes, if you look carefully at these signals, you only see the solid lines are the ones only used for quantitation. And the ones that don't really elute the same, or like the interference correction, isn't used. And you can see only the monoisotopic and the isotope plus one is used. And if you can verify this, you can look here and expand this. And only the ones in blue are used for the quantitation. So Y8, B4, and B3. And so you can see this is solid, Y8, B4, and B3, and then these are not used. Even though they're used for the identification, they're not used for the quantitation. And maybe these are different with DeepQuant turned on. I have no idea. We could take a screen capture or open them side by side and see, but we're not going to do that right now. Okay, let's just look at one more. You could see some of these are pretty low abundant, but they're still good, I think. Let's see, XIC graph. Let's look at, okay, so that looks good. You can also look at the XIC graph, which I like to kind of see the intensity, the viewing of the data overrun. Where'd it go? And so just remember, just because we're looking at this one now, just because it looks a little janky in this one, it may look a little better in that one. You can see how these 200s look better than the 50s, which you would imagine they do. Okay, so just because it looks bad in one run doesn't mean it looks bad in every run, so just keep that in mind. And you can see, so look at here, you see this dashed green line here. This is one that's not used in quantitation because you can see how it doesn't, it doesn't look like it elutes quite right. Kind of looks like it's okay with the 200s, but look at the 50s is terrible. So you don't actually want to use that for quantitation, so it's good it removed it. Whether DeepQuant did that or not, I don't know. Okay, so let's remove that. And so let's look at this one. So you can see it's centered around 0. It's trying to do the normalization. You can see, obviously, as you go down in abundance, it's not what you want. Is you want it really tight here, but you're never going to get that because these signals are kind of lower in intensity. So this is a good example of, what you can expect. And so what we're going to do is we're going to go to analysis, and we're going to look at settings. And let's see, we're going to turn off normalization. So we're going to turn it off. Boom. Okay, and then we're going to get confirm, and we're going to see what that happens. Now, there's one thing about Spectronaut I don't like, and I hope they would change this, but I don't know why. That's version 19, so they could have, I don't know. They've had 19 opportunities to change it, so they haven't yet, so I'm not holding out hope. But what I would like is once you turn off normalization, you should still be able to see the pre-normalized values, which you can't. So that'd be really nice to see, but when you turn off normalization, you can't see it. You could still see the tick overlay, so you could see some things up here, except for my weird green sample, which I should probably remove from the experiment. All right, so let's go back, and we're going to, one thing we forgot to do, which I forgot to do last time, is we are going to turn off DeepQuant because we're going to look at that later, and just give it a couple seconds to redo it. And remember, you can do all of this with the viewer, which I really like. All right, so unfortunately, we're not going to look, we can't look at the normalization because it's gone now. But now let's look at some signals here. Let's just pick this one. Let's do this one, AAA2. I remember this one's a pretty good signal. Number 3, charge state 3. So just a reminder, these are the peptides. If you expand this, this is the mass over charge. These are the fragments it is using. And then here is the charge state. So this is a +3. And we can open this again, and we can say a cross run. And we can look at precursor versus protein. And here we go. So this is non-normalized. So you can see the 200s are much more intense than the 50s, which is what we expect. And let's not make that full screen. Okay, so, and you can again see here, see this blue, how it's dashed. That means it's been interference corrected out. So the algorithm does not think it's very good because you can see it's kind of has a signal outside the area that it's using. So that's good. Okay, so this kind of looks like you would expect. Here's another one. You can see lower in the 50s, higher in the 200s, just kind of what we expect. Same here. That's good. This is kind of a crappy signal. Let's see how that looks. See that protein quantitation is not very good. Okay, so you can see here's the precursor, and you see how they're higher in the 200s, just like you would hope. You would hope they would because we loaded 4 times as much. All right, let's see here. And here you go. Here you go. Boom, just what we expect. And let's see how close we were to, let's look at the LFQ bench here. Let's see if it changed the principal component analysis. Sort of, maybe the 200s are clustering. It's hard to say because it's a relative signal, right? So let's look at, the volcano plot. You would expect, boom. You can see when you're non-normalized, this is exactly what you would expect, right? You'd have everything pushed in one direction. Let's see, you can look at the candidates, and I like turning off, well, we can keep the log on because you'd expect it increasing by 2, right? Log 10, oh, that's a log 10, so let's turn it off. So log 2 would be more interesting. Okay, so you see like 5,000 of 5,445 are differentially expressed. We expect everything to be differentially expressed, so good. It's working. All right, so that's good, that's good, that's good. Mass spectrometry works. Proteomics works. We loaded in 4x the material. We see almost everything changing, so good. Everything's working. Good, 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 good. All right, that's exactly what we want. All right, so let's look at the LFQ bench. So I forgot to explain this. So what the LFQ bench does is if you were to make like a 2 spiking experiment, and you can look up this paper. There's an actual paper called, I think, LFQ bench. And so what that does is if you spike in 2 species, like it's think there's 2 species here because we have some bovine contaminants and then a human. And so what you do for this experiment is you spike in human at like a 1-to-1 ratio, and then you spike in E. coli, or we're going to do salmon. And when we do human liver and salmon, we'll show you the results. And you could see if this was 100% correct, this would center over a log 2 fold change of 2, which would be a 4x change. You can see it's not. It's more like, I don't know. Let's see if we can zoom in here. About 1.6. Okay, so about 1.6. So it should be 2, but it's at 1.6. And maybe my bad pipetting skills. And if you get, let's see, show all, show default. Okay, that looks good. And you can see, again, this is like an M over A plot. So as your intensity increases, you expect the quantitation to be better, and that's the intensity of the signal. As the intensity of the signal gets closer to, signal to noise, you can see the quantitation's less precise. And you'll see this all the time. So the closer this is to 0, closer this is to 2, this is better. I don't know what this line is here. Must be something. Okay, so let's see if we can fix that. Oh, we did change. I don't think we changed this back. Okay, so we're not doing any normalization. We could turn on deep quant, see if that helps. Spoiler, I don't think it's going to help. But again, this is kind of a weird experiment. When I do a proper spiking experiment, I'll test deep quant again. I don't expect deep quant to work this well because this is kind of an unusual proteomics experiment, nobody really does this. Um, okay, so you expect to load the same amount of material. And let's quickly look at the LFQ bench, and let's make sure this display, and you can see it's worse. So it should be centered at 2, and it's more about 1.2. I think it was like 1.6 before. So it actually made it worse because we want this to be here, and it's not. But I don't expect deep quant to work for such an artificial experiment like this. So anyway, I'll try it with a spiked in experiment and see if that's better. So we're going to turn that off. And you can also play around with your quantitation settings. You could turn on imputation and see if that helps. You can change the LFQ method. I think it's max LFQ. You can change the quantity type, see if that helps. Exclude all multi-channel interferences. Share between heavy and light. We don't have any isotope labeled stuff. Only specifies whether the interference correction algorithm only identified peptides for training. I don't know. You can play around with all of this. The data is available. Let me show you where it's available. And if we go to BioShare, and I'm going to put this link in the show notes. Is this show? I don't know. Anyway, this is where it is, and this has the Spectronaut file, which you can get from the viewer, and then all of the not raw files, but the compressed raw files that you can use from Spectronaut to get the XICs if it's complaining about it. Sometimes it complains about it, sometimes it doesn't. Some of these signals are better than others. Runs. Okay, and that's because I have 2 of these windows open. And you can see, it's better. Looks good. Okay, so that's how normalization works. We have a couple new features in Spectronaut. One I really like is the protein verse, precursor verse protein quantity. I think that's about it. A lot of the other new features are the increase in sensitivity. We have been seeing 15 to 20% more IDs with 19 verse 18, which is really cool. Let's see. Most of the other new features are within the PTM workflow, so I will try to show you that later. And you can see I'm getting a better results with the 200s. So the closer these bars are to each other, the better. So this, usually people like to look at things that are under 20% CVs. My CVs would be better if this one worked well. So why that is, I don't know. I chalk it up to pipetting errors. Let's see, data completeness, run identifications. I think that's it. I think that looks about right. And you could see for protein, I don't like how it spreads out like this. Okay, you can see where's protein groups right there. And you could see, we'll sort this from lower to higher. And you could even see as we get more proteins with 200 nanograms than 50, as you would expect, but not much more. So like this one, this might be my bad. This is obviously my bad pipetting one. We're identifying 5,200 proteins for 50 nanograms and 5,400 with 200. So it doesn't scale the way you think it does. And so you may not, you're not going to identify 4 times as much stuff with 200 nanograms versus 50. That's just how it always is. Okay, so that's it. I think we looked at one new feature in Spectronaut 19. The other features are, we can go here and look at them. So major improvements over direct DIA. We have seen this. So we have seen at least 11% more, maybe up to 30. 40% improvements in performance metrics on deep learning models. Okay. Option for deep quant, which we did. 40% faster on the timsTOF. It is a lot faster. You guys don't have to worry about that since we do it for you. RAM reduction, you don't have to really worry about that. That's kind of more on my end. File size is reduced by 80%. Oh, up to 80%. That's cool. I didn't notice they were smaller. Temporary hard drive requirements. Okay, that's more on my end. Diagonal passive. I have played with this from the. That's a new way to acquire data on the timsTOF. Unfortunately, you need a license from Bruker in order to do it, and we don't have that. So hopefully we will get that and try it out. Improved support for labeled DI workflows. We don't do any isotopic labeling. New features for PTM modifications that are actually, that's really cool. I'll go over that when we do a phospho enrichment experiment. Let's see, command line stuff, new visualizations, peptide versus protein quant. I really like that. Thank you, Biognosis. That was super cool. Some PTM stuff we'll go over. And another video. Let's see, that you don't have to worry about. Analysis settings, this new stoichiometry. We'll go over that. I don't really know what it does. New input strategies. Let's see, a hybrid analysis workflow. Let's see what we have here. Spectronaut 19 uses only MS2 quantitation for differential abundance. Previously, it used both MS1 and MS2. That's interesting. I've tried to get some clarification on this. I haven't got any yet. Especially for single cell, you want to use the MS1 signal because it's going to be a lot more intense. And when you get really, really low, like into the picogram levels, you definitely want to use the MS1, or at least that's what people think. At least that's what, I don't know, 15 or so people who do single cell think. I think. I don't know. We'll see if I start doing single cell. Anyway, that's the new stuff in Spectronaut 19. This is kind of what normalization does and what to expect. I will put the link to the BioShare so you could download this and play with it yourself. So just remember, normalization is super important. You expect almost all of your samples to have the same amount of protein in it unless you're doing an affinity enrichment or some other experiment. But for normal, bottom-up proteomics experiment where you're doing a differential expression on different conditions, you expect your total amount of protein to be the same. And normalization will correct for that. And you can see we had some issues when it did up to a 4x. Normalization, it didn't work as well as, it wasn't perfect, and nothing is. So, but anyway, it's good to get an idea of where things start to break down. And I don't even think it broke down. I think it did a really good job for loading 4x the amount of material. So if you accidentally add 4x amount of material, I think normalization will fix it. We'll try and fix it. So anyway, thanks everybody. I'll try to post videos more often, and thanks for watching. I'll talk to you later. Bye.